Thank you for inviting me, Magid. Yes, my name is Ahsan Qamar. I'll be talking about ontological foundation for building automotive systems, especially system design and testing, which is the area where I work in. I think I will just carry forward what Dave presented in the previous talk on um, taking the models and determining what questions they must answer, because um, that is also key KPI that we observed in our own practice of models. So this talk is going to focus on ontological perspectives, and also I would like to, in the end, talk a little bit about how do we think of using models and how, in the sense of test-driven development and software development, those practices need to come more closely together. So I would try to leave a lot of time for questions in the end, because I do want to take community's feedback and what do other people think of similar challenges. So that's the agenda. We will talk about, we'll start with the first topic, which is the, in my opinion, directly related to ontologies, data collection. So, and I'll talk about it in a few seconds, and then we'll talk about the topic of tool interoperability, which was very important for us to get our infrastructure and our methodologies working. And then I will wrap up with a high-level view on models in test-driven development workflow. So let's start with the first one. So data collection, from the perspective of data collection, all of these vehicles that are in the field are agents or devices that you would want to collect data from. And then the question comes, and many of these vehicles are from different manufacturers, right? So then the question comes, if you want to have a standard way of querying devices for, is my audio still fine? I heard some echo. Can someone? Okay, so the question comes, if you want a standard way of querying data from these vehicles, and they are made by different manufacturers, let's say, what can be a standard way? Because every builder will have specific networking in their vehicle, and then the networking may have specific messages on those networks, and those messages will be very specific to how you want those messages to be named. So if you want to run some intent, as an example, so you want to run this intent, and intent is some business logic you want to run across all of these agents. So find me all of this, find me an agent that is violating a speed of 70 miles per hour, or find me agent that has violated this speed. How do you run this is the question, because the speed as a variable needs to be defined in some standard form. And if vehicle 1 has speed, it should be the same variable that vehicle 2 has. Now, without some basic definition of these variables and in an ontological foundation for how they map to speed, which is coming through an Ethernet packet versus speed that is coming through, let's say, a CAN transmission, you would not be able to run these intents, and you have to dig inside the stack of these vehicles and figure out what exact software variable or network variable is carrying this data. And the same applies for, let's say I want to write a simple query. If there's no passenger in the vehicle, start recording video. The has passenger property, how do I make sure I can consistently use it across all of these agents? So one of the things this is where I really think the ontologies really shine, is there's this effort which we also participate in from Connected Vehicle System Alliance. And in here, we have tried to think about what's called vehicle signal specification. And what it does is it basically defines a knowledge graph of what a vehicle shall be looked at as. So I have a vehicle which has a property speed, and it has a cabin element which has seats and doors. And the seats has a property has passenger, and door has a property is locked or is open, and powertrain has a property range. A lot of people are concerned about range of, especially for electric vehicles, and so on. Now this is just a snapshot, but ultimately, if we adopt this and internally we can do a mapping of is locked property actually mapped to an Ethernet SOA property, while has passenger property maps to a CAN message inside the vehicle, then the mapping can be done for each specific builder differently, as they may have, let's say, a Ford vehicle has passenger um, as a CAN message, while some other vehicle has it as an Ethernet packet. They can do this mapping internally, while everyone else who is the consumer of it, people who have to build these intents and query, send these intents to all these vehicles, they can build it by the standard specification, which I think is a really powerful tool for how you can be building business logic for several different devices, if you may, so that you can query it across. And now the power of this is that if the same specification is adopted by different manufacturers, then you can use it across those vehicles across those manufacturers as well. So, which I think is a pretty neat thing to do. So this is you may see if you folks, anyone of you have been in the conferences for Connected Vehicle System Alliance, you'll see a lot of work has happened on how we can collect data based on this specification. Now, another example of this is in tool interoperability, and the fundamental principle remains the same, right? So what is the problem we want to solve? Um, our engineers works on from user experience definition to system design to system safety, quality, system test, software test, manufacturing, and operationalization. And of course, these tools, these areas are supported by a plethora of tools. Now, how do we enable us to have a good understanding of where the loopholes are in the design of the system? Is there a real critical chain when we go from the left side to the right side? What is the critical chain and what is the critical path to the system? Now you can look at this from another perspective where you will have tools that can define your requirements, and the requirements may go from experience level requirements to system level requirements to software level requirements. And they may map to your system design as artifacts, such as your system state or your system action, or at the high level, let's say a use case of the system as well. And similarly, the requirements constrain or are also the aspect of safety, where we try to analyze the design of the system and look at it from malfunctioning behaviors that could cause hazard, and then define mitigating actions to mitigate those hazards. Um, Similarly, in failure mode analysis, where you look at the same design from the perspective of it not meeting its design intent and causing failures because of environmental disturbances. And then you will end up with mitigating actions that essentially lead to requirements, additional requirements. And then in the end, we want to run tests against our requirements to see that whether we can operationalize this system or not. Now, what happens is that some of the questions that people ask span multiple of these domains. So are there requirements that tie to functions whose failure mode is greater than 8, where we don't have a mitigating action? So this is a question that people commonly ask. How do you answer this question? Because each one of this graphs is in specific tools, and the lines that I drew across these tools don't necessarily exist seamlessly. Similarly, another question, so let's say if you take a slice of this graph from left to right, and you think there is two variants that use two different slices, but there are common pieces among those. Like, how do you answer that question? So there is, of course, horizontal level of the question, and then there is a orthogonal level to that, which is the variability problem on the same question. And again, this spans across multiple tools. So again, if you think from ontological perspective, one way of trying to think of this problem is to build some digital thread repository, which basically will be your backend for that you will mine and query information from all of these design repositories as on the top, and you will do your secret sauce here to then to provide to a user to some user interface answer to the questions they're interested in. So which means that there's work needs to be done here on the backend side, and there's work needs to be done on the front end side so that you can design visual analysis tools that user can just select questions that they want to answer, and it will show answer to those questions for their project or for whatever they are working on. Now, the backend design is similar to ontological problem we saw before. So you have data in SysML models. This is a small example where you have, let's say, clearance between two parts defined. So you have a part one and part two, and there is a clearance requirement defined between them. Similarly, you have the same same projection of that as a field clearance requirement in JAMA, which is the requirements tool. Now, the data on the left side should conform to what I would call a parts ontology, which defines how parts can be connected to other parts or how they can be contained inside other parts. And then the data on the right side should conform to the requirements ontology, which defines what is a requirement object and what can it be satisfied by, what can it be tested by. So once you, as an ontologist, you define those ontologies, and you then start defining how they map to the corresponding tool specific vocabularies, you can reach this solution where even if there is a requirements in multiple tools, and I just took this as a example to illustrate the point that even if you use multiple requirements tools, let's say in your organization you use Doors and Cameo sometimes, and Simulink requirements the other times, and Team Center the other time. Because you have a requirements ontology, you have a way across all of these tools to comply to one single ontological definition. So even if in one tool I call the requirement REQ, and then the other tools I called it elephant or a cat or a dog, I can still infer them as all requirements. And this requirements ontology is what will power your backend when you infer information from these tools. Now you can apply it to multiple tools in the landscape. So I have here requirements ontology that is spanning across different tools that help capture requirements. That doesn't mean you should be using all the tools, or you may be using one of the tools. You may have a test ontology, you may have a FMEA ontology, a safety ontology, and simulation ontology. And then they are probably built based on basic ontologies that exist already by standing on the shoulder of giants who have already done the work in those areas, such as IEO or the BFO ontology. And this essentially enables us to extend the basic ontologies and make them more specific towards the domains, and then use the domain ontologies, such as the RM or the test, towards inferring information from these tools, parsing that information, and then storing it in the backend. Once you have that backend, you can, of course, then start saying, okay, now I have a mechanism to take all of the information from several of these repositories and stitch it. Now I can build a user interface, which the user will go and write this query, and the interface is going to boom, um, give the answer. And of course, you have to design this user interface because you can't just show triples or raw data to the user. So they have to be presented in a form that can show the pattern the user is looking for. For example, in this case, the severity lies in this set of functions in this specific domain and not in the other set of functions. So your user interfaces should be tuned to answer such kind of questions. Now we have experimented and built a couple of these, and they are published in these papers that you can look at. Um, Ultimately, what happens is that once you have solved this problem of multiple tools and data and your user interfaces, then essentially you have this digital thread navigator where you will move between multiple of these hexagons. And this digital thread ecosystem is going to help you move from when you are looking at this specific set of information, how do you seamlessly move from here to design and then see that correlation perspective still maintained. And that's where the UIs really shine, because I can be standing on a design element and seeing how does it impact safety or how does it impact testing. So to show an example of this, this is a tool that we had built as a prototype example a couple of years ago, which is basically parsing our design information and our failure analysis information. And it's displaying to the user several different patterns around those. So the users query different projects, and then the users are trying to find which of these projects match the pattern that I'm looking for as a question. So for example, this specific element I'm selecting right now is affecting this functions in my project. And all of these functions now I need to take into account to see whether I have mitigating actions against that. And I can, of course, show them in different views so I can see end-to-end traceability, which I think you will see happening in a few seconds right now. So now you can see end-to-end traceability on the left side. This is what everything is impacted. And on the right side, this is what everything else is impacted. And once you understand that, then you see that what is your critical path? What is your single most element that affects most of the things that you must address first? And that's what these things enable you to do. Okay, I'm going to switch gears because I'll be running out of time soon. My final portion of my talk is about how we should be thinking of as practitioners of model-based systems engineering, as ontologists, as system designers. How should we be thinking of this? Now, I think of this is my example. I come from controls and robotics background. Ultimately, the vehicle can be broken down into a set of control systems. So we have control systems, and we design these control systems to control these plants, such as windows, lights, wipers, enclosures, or control the battery or longitudinal or lateral motion, or autonomously control the autonomous planning and localization algorithms. Now, in terms of designing them, we write, of course, the design is not simple, right? So you have designs that's captured in SysML models, which define the behavior, such as in a state chart or an activity diagram. And you also have structural interfaces captured in the same SysML models. So now the SysML models define your intent in the beginning, which is based on an experience we need to provide. And because it's part of a workflow that we want to, let's say we want to build a specific control system in the next 3 months, and we have a work item against it, which goes from system design to software to test. This work item is constrained by the requirements, which we actually determined based on our initial work in the SysML model. And these requirements have to be verified by the test case, which is running on the source code, which is in our build repository, which then is executed through some test execution algorithm and infrastructure, whichever you choose. Now, in this view, we think of models as one point in the whole chain. But ultimately, going from models to the actual build is a number of steps, right? And as a practitioner, I ask a question: is there another way for us to think about this, or how can we think slightly differently as well? Now, this is a slightly different view, where I see SysML and the requirements as basically, once we have identified what we want the system to do and how shall the system do it, ultimately I need to capture it in some formal spec. Now, some portion of that formal spec may come from formalisms, let's say state charts, which is embedded in SysML editor. Others may not. Others I may be using things like Gherkin, where I have specified a Gherkin code says that I have given vehicle speed such as 80 when alarm is armed, then the violation is true. Now I can do a pipeline against this specification and generate an assertion in my test code, which will be true or false once it's run against my build repository. Now, I may have inferred this from my SysML model or a set of requirements, but ultimately, if I think in this way, then I will start referencing, let's say, my JAMA requirement URL as a trace link to my formal spec, because that's what it's constrained by, or my SysML model state chart inside the formal spec. And then once, of course, we have the assertions coded, we can run them against a virtual target or a hardware target. Now, I see this a slightly different way, although this can be, of course, debated. But in my opinion, the focus of this is on what's outlined in this blue outline, versus I think there is multiple areas of focus in the previous view. So I will give you this as a food for thought, and I will, of course, want to hear people's feedback. So I'll give you 5 minutes for questions. Yeah, if there's any question.
We have 5 minutes for question. So if you are online, please, you can speak up or in the room here. I have a question for you, Ahsan. Can you speak about the practice of using ontologies at Ford at the moment? Like, how are you using them today?
Yeah, so the two examples I provided in the beginning, there is the use of ontologies which we formulated for the sake of the tooling problem. And then there is also the one that I've talked about in terms of vehicle data collection. So they're used for both use cases. Is that your question again?
Thank you, Ahsan. We have another question.
Hi, Ahsan. Michael Halverson, University of Alabama at Huntsville. You were speaking, collecting the data from a variety of different cars, different makes, different models, different producers. For the collection of data that might be called cat, elephant, requirement, whatever, you still have to go through the OSI model. Is the association of standardized data with standardized packetization locations, is that the point here? It doesn't matter what it's named, it's the location of it within the packet?
Yeah, I mean, if you go the higher levels of stack in the OSI model, ultimately the point is that a hardware abstraction layer element shall not influence how you collect that data. You can change the hardware, and let's say instead of an encoder, I'm using a laser to determine speed, but my speed property should still stay the same at the higher level.
Right, but I mean, if you've got all these different cars from all these different
Mhm.
manufacturers, they're going to sequence their packets in different ways with different sets of information, however they choose. And then if we standardize the ontology, we standardize the terms here and try to collect them from all the different locations, is the idea to have the ontology associated with some packet standardization that everyone is translating to?
Yeah, ultimately, people will have translators from that to their specific implementation, yes.
Okay, thank you.
But they will all conform to the base ontology.
Have 2 more minutes. Question?
Son, this is Giancarlo Guizzardi. Thanks for the talk. I was wondering, some of the predicates or classes, let's say, that you had in your example, like the door being open or closed, or the car being over the speed limit, for example. So these are kind of dynamic classes, right? So how do you deal with that in OWL, which is essentially static? Or do you just model that, but you don't do reasoning with that?
Yeah, that's a great question. So I think in terms of specifically where the VSS work stands, we have modeled it fully in order to basically our first goal was to understand the mapping of our internal with respect to the previous question and from our stack to that, and either if we can make it work as a client sitting on a cloud to basically start querying these intents. We haven't yet done a lot of reasoners running on the same engine, which is what you are referring to.
Okay, thank you.
Okay, I think I'd like to thank Hassan for the great talk.